Okay, good evening everybody, and welcome to our ninth and final evening meeting, technical talk for 2016. My name is John Carr, I'm the Yorkshire Region Chair. This is my last talk, so I'm handing over to David Richardson, so I'm sure most of you know. So we're not expecting any fire drills tonight, so if there is the alarm does go, clearly follow David out the door, or me, whoever's first. CPD certificates, if anybody needs one, please just drop myself an email and I'll sort that out for you in the next week or two. And there is a record of attendance form, so that will be coming round. If you could just fill that in, that would be great. Okay, so tonight's talk, sort of cyber design of connections with the use of perforated beams, whatever that means. So by Konstantinos Daniel Tsavdaridis. I'll just say no more than that and hand you over to Kostas. Thank you.
First of all, thank you very much for coming around. I can see many faces, well-known faces, our students also, they're here. As John said, the topic I'm presenting tonight is the seismic resistant design of connections with the use of perforated beams. So obviously it's about research, most likely, most of the research that I've done the last decade or so. I'll try to keep the surface of the research and not go into the great depth, but get the main message out of it. The contents of the presentation, I will try to engage at some point two different concepts. So I will start from the design of perforated beams in the lightweight construction, and then I will bring to the discussion the seismic resistant design of connections. So I'll try to engage these two through 5 different case studies. And then I'll conclude with some main messages that we have at the moment. Obviously, all that is an undergoing research, so there's much more to be done in the future. So it's quite interesting to actually see that the last decade or so we have introduced quite a lot of interesting words in our vocabulary, such as efficiency, structural performance design, sustainability, resilience. In fact, we live here in the Institute for Resilient Infrastructure, adaptive and flexible design. All these keywords, to me, they translate as optimization. What we're trying to do all the time is to optimize the performance of the structure in terms of structural performance, in terms of economy, cost, efficiency, as well as the manufacturing performance of certain members. So it's about different criteria that we try to optimize every single time. And being myself a structural engineer, back in 2005, I started working on perforated beams a lot because being, as I said, structural engineer, not a material scientist, in fact, I was focusing on the topology of the material in order to improve the structural performance of certain members. So how we can make sure that we have light members which they are very stiff and very strong. I don't think that I have to go really thoroughly about the advantages of using perforated beams, but for those that they haven't used them so far in their life and they are mainly focused on concrete structures, main advantage is that we can integrate the services through the beam, meaning that we decrease the structural depth per floor, so the floor to ceiling height is decreased, and by that 10 to 15 or 20 centimeters decrease of the structural floor, we can gain extra floors when we multiply times the number of the floors that we have in the building. So the main great advantage is that one. But at the same time, we can have longer spans, meaning less columns, less foundations, less maintenance. There are some studies that they compare the performance of the in terms of cost. perforated beams with the pre-stressed concrete design, and we can certainly say through these studies that we have managed to have a cheaper design. And the installation cost becomes cheaper because of the light members. A very good comment also is that having this opening on the web of the steel beams, we have access for maintenance as well as for the welding, which is not happening when we have really huge plate girders and we design a solid web. Now, back in 2006, the American Society of Civil Engineers, they published a very interesting study that they focus on the performance of castellated beams, so perforated beams with hexagonal openings, and they said that once you can count the number of the beams that you have in a project, and if those beams are spanning more than 12 meters, then you have an economic design. In fact, a more precise study came up later on in the same year, and they talked about groups of hundreds of beams. So if in that same project you have more than 100 of beams that they need to be perforated, then you have dropped significantly the cost of the structure. And again, around 12 to 15 meters span is the ideal one that you should have when you use perforated beams. So if you have something more than that, if you need something more than that, and you need a lot of them, then definitely is the most economic solution, because everybody is actually wondering whether the use of the perforated beams actually booms up the cost of the structure. But that's not the case according to the American Society of Civil Engineers. So a lot of study happened in the past, and in 1994 SCI, Steel Construction Institute, published the P100 publication for the design of composite and non-composite cellular beams, and more recently, after a lot of work that we have done, the design of composite beams with large web openings has been published. Now, since 2006, all that information triggered my interest a lot, and I started working really effectively, I believe, on the design of perforated beams with standard and non-standard web openings. I was looking at closely spaced openings, really large diameters, and all the different failure modes which are associated with the design of perforated beams. We have to appreciate that we have 2 or 3 extra dominant failure modes when we introduce perforated beams in our design. Trying to understand what is happening in the vicinity of the openings, we're looking at all the stresses, but always the aim was to introduce all that material to design codes, and the practitioners can be using them. So at the end of the study of each one of the studies, we produced shear moment interaction curves, so practitioners can go straight away and use that information and design their own beams. One extra thing that we had to make sure that is very clear and comes out of all that research is identify which one is the key parameters, geometric parameters that affect the behavior according to the failure mode that we're looking at. Because there are a lot of parameters, as the SCI P355 document characterizes perforated beams. It says that it's a very complex design, and there are a lot of failure modes associated. We had to make sure that we understand the best of its design. Going a little bit more in depth in what is happening, when we have perforated beams, we're always looking at the formation of the plastic hinges. So the black knots that you see there, in fact, are the plastic hinges concentrated in the vicinity of the opening, all around of that edge. When we use the old design of castellated beams, the position of the plastic hinges is a standard one, is always at the corners. When we introduced, though, the design of the cellular beams, so perforated beams with circular web openings, then it was really interesting to see that the position of the plastic hinges was changing, and that makes our life and the design much more difficult. So that's why we called that distance between the top plastic hinges of the top T-section as critical opening length. And this is exactly how the P355 is also calling it. And you can find that as a C or a L knot. We need to know that position of the plastic hinge, because then you will be working out the capacity of the perforated beam of the cross section at that angle. Now, something that we can observe straight away from that picture here is that the position of the plastic hinges on the bottom picture, the one is dealing with the perforated beams, the cellular beams, sorry, is not symmetrical. So along to the central line, the position is not the same. And in fact, while you're moving the opening along the length of the beam, so you're changing the shear moment interaction, those angles do change. That makes our design even much more difficult. So my task was to use advanced tools, finite element analysis, as well as more advanced tools doing all the optimization. We ran back then around 6,000 models using tools that they are mainly used by the aerospace engineering, like the Altair engineering company, and Beta Chi systems, which is used mainly by Formula One and automotive engineering. So we use really advanced tools to find out what will be the most and the best web opening shape. And we came up with what I like calling an elliptically based web opening, which is in fact is a combination of two semicircles and four lines at an angle, or two trapezoidals. So that opening, the beauty of having that novel patented opening is that we can control the plasticity. So we actually know where the plastic hinges will take place. But at the same time, we do not move the plastic hinges very close to the top flange and the bottom flanges, where there is a lot of stress if we do the stress block method and find out what's happening. At the same time, we have not concentrated those plastic hinges at those sharp edges, where we may have cracking. And all that actually is very important when we look at the seismic resistant design of connections. So a global comparison between the cellular beams, the one you see on the top, and the novel patented ones is that we can have as light beams as the ones with the cellular beams by having more elliptically based web openings closely spaced without compromising the capacity of the web post, hence the part which is between the two openings. And we have a cheaper manufacturing process because by the way that you cut it, in fact, the cost has been reduced. The cutting line, let's say, is smaller than the one we use when we manufacture the cellular beams. It's obviously slightly more expensive than the castellated one, but castellated openings, because of these sharp edges, they are not used anymore. But the most important, the far most important aspect for us is that we can control the ductility, we can control the position of the plastic hinges, and the critical opening length, which is the dominant parameter, as we'll see later on. Now, all that study and the studies that we can see out there from people that they use them every day and they use all the software provided by the manufacturers, they always look at the scenario where there is a simply supported beam. Obviously, if you design for seismic resistant design connections, then you have to look at moment resisting frames and plasticity, the position of the plasticity. So, pausing a little bit the presentation and moving to the seismic resistant design of connections, I like actually this video. I used to have it, some of my students have seen it already. So, we have to appreciate the structures move, so we cannot really design structures as a static way, and we cannot really think that the design that we have done is quite simple. We have to understand what is happening when buildings do move. In fact, we should allow for some ductility there. We design the structures to be elastic, to behaving linearly, perfect, but we should allow for some ductility, because structures will need that ductility, especially in the case of an earthquake. But also it happens sometimes in the case of excessive wind loads like tornadoes. Now, a point of reference in civil and civil structural engineering, especially those that they work with steel structures, is the two earthquakes happened in 1994 and 1995, Northridge in the US and Kobe in Japan. So these two earthquakes, they actually changed the whole philosophy of how we design the moment resisting frames. Especially the second one, because we had a lot of people lost their lives. As you can see from Wikipedia, 6,500 people were killed. By these two earthquakes, there was a whole new era in the design of connections, and all that started from the SAC Joint Venture in the United States, where they introduced the new design connections, new connections for design that they in fact call them post-Northridge and post-Kobeck connections. So what we're looking at is obviously a building which is shaking, and they had to investigate which is the part of the building which is subjected to the highest forces and which is the part of the building that fails first. And they found out that although the columns of the ground floor, they were the ones subjected to the most shear, base shear due to an earthquake, connections failed at every level. And more particularly, the welding of the connections failed. And even more in detail, what has failed first was the connections, the welding, which was in the compression zone. So they started investigating a lot, different types of connections that they found in those damaged already buildings, and they found out that they were a huge cracks along the length of the welding, but not only the ones which are subjected to compression, but also the ones that are subjected to shear. And those welds, you can assume that they shouldn't fail. Now, it was even more interesting that, in fact, we got failures from the zones in the vicinity of the welds. As you can see in this example, the weld has not failed, but the heated zone around the weld has failed. So that triggered more and more research in order to understand what's happening. So the main conclusion from the SAC investigation, which lasted for more than 5 years, was that the welds and the heated zones of the bottom flats, they were subjected to high inelastic strains, which take place mainly in the facade of in the face of the connections, in the face of the column flats. Hence, we had to introduce the ductility concept in our documents. So instead of designing something like that, we had to move to something like that. That means that you need to reduce the capacity of the building, which is not ideal always. And reducing the capacity of the building, you have to increase the ductility. You in fact increase the ductility. So this reduction factor R is in fact the ductility factor that you need to be using in the structures. In certain cases, we have to reduce the capacity of the building by 80% in order to allow for that ductility. So the potential plastic hinges that we have as we all know very well, in the connections is either very close to the connection at the bottom side of the connection on the column web, and in that case we get the well-known failure mechanism, which is called story mechanism, or in the story drift, or soft story. In the case we have the plastic hinge formed in the web panel zone of the column, then we have the shear yielding of the connections, and most likely we will have failures of the components of the connection. And in the case we have the plastic hinge at the face of the column, as we saw previously, we have a more desirable failure, as long as that plastic hinge is away from the actual components of the connection, such as the welding and the bolts and all the other clips or plates or splits that we use in our particular connection. So the idea is to move the plasticity away, mobilize the plasticity away from the connection somewhere around the beam. Obviously, we cannot really move it a lot far away, but we have to be very precise on what is that S end distance. So as I said, the SAC Joint Venture, they came up with a whole new methodology of how we should approach steel structures when we design them for the seismic actions. And in fact, they introduced a number of state-of-the-art reports, which they were produced after a lot of tests, a lot of fine element analysis, and a lot of reliability also investigation. So we had to make sure that all these things that we're producing, they cover the whole range of connections and specimens that we may have. According, the design criteria have changed. So these are the FEMA publications that came back in 2000, around 2000. the first ones published, and since then we get more and more of them. Some of them are dealing with a moment frame building, some of them they are specifying on rehabilitation and strengthening techniques, and so on and so forth. More lately, that information was introduced in the Eurocode 8. It's not there yet, it's not completed, but most of the information is coming on. So what that tells us now is that we should not, first of all, we should not treat our structures as elastically, but we should check the hysteretic behavior of the structures. It's extremely important. And we should have some dissipative parts in the structure as a passive mechanism to allow for that, for all these stresses to be concentrated and dissipate the energy comes from an earthquake. Now, these parts may be either the structural members or the connections. In the case that the dissipative part is the structural connection, then the members around it, they should be overstrengthened, and the vice versa. So if the stresses, we allow the dissipative parts to be the members, then the connections themselves, they should be overstrengthened. So that is the main lesson that we had through all these investigations and what the Eurocode 8 nowadays is proposing to us. So the rehabilitation methods that are proposed by FEMA, first of all, is what else? By strengthening our connection. So start adding plates and welds and stiffeners to make our connection stronger. But there is also the opposite concept, which is making some of the parts of the structure weaker. How we cut some parts of the flanges, and I'm sure that you all know the RBS connections, the reduced beam section connections. Much more recently, I would say after 2010, 2011, the first investigations came to the light where people are actually cutting the part of the web to mimic what the RBS connection is. But things are now changing because, in fact, we cut a completely different part of the beam. As a first approach, I can certainly say that the one on the top is quite expensive because you keep on adding plates and manpower there to do a lot of work and add all these stiffeners. In fact, you make your structure heavier, which is not in our aim. We're trying to make our structure lighter, in fact. And in that case, the effect of the seismic will also be smaller. In the case of weakening between RBS and RWS connections, I would say the price is pretty much the same. There is a slight difference, obviously, in the way that we cut the flanges and the webs and the precision that we need. And that's why I would say that the RWS connection is slightly cheaper than the RBS connection. Other strengthening techniques are shortening the spans, adding beams, replacing members, or adding post-tensioning using external pre-stressing, enlarging sections, as we said, increasing the welding again, which is not ideal. As we said many times, we don't really need that welding. FEMA 350 particularly came up with numerous different design connections. To some of them they give some funny names as well. They are, in all of them, they are bespoke designs, so you have to be using them in particular applications. You cannot really use them globally. So coming back to the EC8 and RBS connections, those are the ones that they have now the priority to be introduced in Eurocode 8. So we did some other investigations also to make sure that the UK sections and the European sections will also follow all these observations that we had from the American sections. But I would like to highlight three actually things that we have to consider when we use RBS. First of all is that the cutting of the top and the bottom flange should be very accurate. In the case that we have some eccentricity between the cutting of the top flange to the bottom flange, we have straight away some out of plane movements after this zone is stressed. So that will lead to lateral torsion buckling, and we will not be able to dissipate the energy we want because of the lateral torsion buckling. The next thing is that RBS design is very limited. So what we have seen so far in terms of publications and what we came up as a design methodology is a very limited in terms of the radius that you can cut. So you cannot really use them in all sections, and it has to be specifically at that location. You cannot move it along the length of the member. But most importantly, the problem that we find out is that you lose the shear, the horizontal shear interaction between the metal deck and the concrete slab and the steel flange, because you're reducing the flange part. So you're reducing that shear interaction. In fact, what the American codes propose, but a lot of designers they haven't really noticed, because they just have 3 lines and they say that, is that the space that you connect the concrete and the metal deck to the beam, you should not allow for shear interaction. So you should assume that there is no shear interaction along that zone. Meaning that the whole calculation finding what is the shear connection between the slab and the steel becomes more complicated, because you've lost that part. However, we have seen different designs of RBS, so people they have different kinds of cut on the flanges, and the whole methodology that we use at the moment is you run a finite element analysis or an experimental result, you produce the moment rotational curves, and then you introduce these properties through spring elements in your structural model, and then you come up with a solution which should look like this. So you should get the plasticity in the distributed in all the beams, instead of getting something like what you had at the beginning. Plastic hinges on the columns and inter-story drift, where the buildings then tilt and collapse completely. So if I can do a very quick comparison between the RBS and RWS, I can certainly say that in RBS connections the shear capacity is not reduced, because you haven't lost anything from the web of the beam. However, you have lateral instability problems, and the time and the cost for rehabilitation is quite expensive, because if it is an existing structure and you rehabilitate the structure after an earthquake, actually cutting those flanges while you have the concrete and the metal deck on top is not as easy as it sounds. On the other side, when we have RWS connections, they are much easier to cut. Just drill a hole on the web. There is very good shear interaction. You haven't lost your shear interaction between the steel and the concrete. You can have that opening as accommodating services, and in fact as providing maintenance and access. So there are some advantages come from the perforated beams to the design of RWS connections. So because of that, we went through certain studies. So I will be looking at 4 different types of connections, starting with a fully welded connection using isolated beams. So we found an experimental setup from the literature review, and you use that one in order to validate our finite element model. We always use the SAC protocol, loading protocol for moment resisting frames, comes from FEMA 350, and we found that our model behaved adequately. And then we produced a parametric study, changing 3 parameters: the web opening shape, the depth of the web opening, and the distance of the web opening to the face of the column. So getting the big picture, just trying to show a few things overall that we managed to gather from these results, is that when we used the novel openings as opposed to the circular openings, we get quite similar results every time. That's good, because the results are consistent. However, when we use the circular openings, while we're changing the opening dimension, we get quite different behavior. What is important, in fact, is to relate how much stress will be moved from the connection to the plastic zone, how much ductility will we gain, and how much capacity we'll lose. So relating the capacity to the ductility is very important, and we have done numerous repetitive calculations to check how much these two relate to each other, and whether there is a linear interaction or something like a non-linear. We can certainly say at this stage that through that experiment, that when we reduce the capacity by 50%, we gain a 30% ductility. Another very important comment was that the critical opening length plays a significant role in the behavior of the hysteretic behavior of the connections. So the bigger is actually the critical opening length, the more is the strength degradation that you get once you run the hysteretic behavior. So that is getting more higher when the critical opening length is increased, and that is not good for the RWS connections using circular openings. In terms of the effect of the depth, now we can see for instance, three examples that all the openings are at the same position, the same S, but we have a smaller and a bit bigger and a very big opening, and we can certainly say that at the bottom case, where the opening is quite huge, all the stresses have been moved away from the shear panel zone of the connection in the vicinity of the web opening. So we have 4 plastic hinges formed in the vicinity of that large opening, and no much stresses at the shear panel zone, which is an ideal design. Again, comparing the plastic hinges and the formation of the plastic hinges, the order of the formation of the plastic hinges, better say, we were very pleased to see that in all scenarios it happens with the same order, so we're not jeopardizing the knowledge that we have already for the cellular beams. And a great example is the one that you see on the left, where although we have an opening, because the opening is small and is positioned away from the connection, there is no any different stresses in the vicinity of the connection. So you get exactly the same amount of stresses at the critical zones, meaning that if that opening is small and away, you're not actually designing an RWS connection. Something which was of a surprise, I would say, is that the web opening area does not play a significant role in the ductility. So it doesn't really matter how much is the web opening area. What it matters is what is the critical opening length. And you can see, for instance, the rotation ductility of 2 different beams, completely different web opening areas. It's 50% higher for the B1 case, but both of them, they give us exactly the same rotational ductility. And on the bottom picture you can see, for instance, 2 again completely different web opening shapes that they give us the same web opening area, but a completely different rotation ductility. So the web opening area is not the dominant parameter, and we had to clarify that because people are always talking about the material, the amount of material which is removed, and they're trying to correlate the results with the amount of material. But it's not the amount of material, it's the location of material which is the most important. So for our case, it's the C, the critical opening length. So getting the big picture, I'm just going to go to the highlighted examples. So this particular one gave us the highest rotational capacity, which is then compared with the lowest rotational capacity, comes from the connection having a solid webbed beam. But more interestingly, we would like to see what is happening in the the moment capacities. And we can see that the 278.2 has been reduced to 135.6, meaning that almost the capacity has been reduced to half. That 50% reduction of capacity gave us a 31.6 increase in the rotational capacity. So that figure, the 50 with 30, in fact, it comes up as the most robust figure that we have at the moment. You reduce 50% the moment capacity, you increase 30% the rotational capacity. So if I can synopsize all the parameters that we played with, the parameter denote the depth of the opening. The bigger it is, more likely is that you will get the veer-and-tilt mechanism, and then you will reduce the stresses from the joint. Oppositely, if you have the parameter S, the end distance, the smaller is the S, again you increase the veer-and-tilt mechanism, the possibility to get the veer-and-tilt mechanism, and then you release the stresses from the joint, and then we propose some openings for these particular connection types. What is very important from that slide is the comment at the very end, which says control plasticity via shear hinges. So I would like to clarify that we're talking about shear hinges and not plastic moment hinges, as the RBS is all about. So through the shear plasticity, in fact, we have controlled the performance of the connections instead of the moment plasticity, and that has to be very well understood. Now, we also looked at some north-risk connections, the welded unreinforced flange bolt connection, WFB, as well-known ones. Again, the same one. I'm just going to skip through the slides quite briefly. So the same similar connection type, different connection type, similar methodology. We again used the SAC protocol and we ran the 32 cycles. We validated our models and we did the same parametric study. And again, you can see, for instance, when we compare the one on the bottom right to the top left, the one with one of the novel elliptically based web openings, we can certainly see that there are some failure modes in the vicinity of the opening, like web buckling and flange buckling, and because of that, the stresses that we had in the shear panel zone have been moved away. So the column, we expect that the column will behave linearly. Looking at the moment capacity against the web opening area, it is interesting now to investigate the monotonic as well as the cyclic performance of those, and because we're only looking at the cyclic, but we cannot really correlate that to what is happening in the monotonic. And what we found out is, by just using a monotonic analysis, in fact we overestimate the capacity of the connections. So you can see the 450 that has been removed has been reduced to 390 when we did the cyclic performance. And that gives me a clear evidence that we should not be treating the connections as definitely as not as linear systems, but not even as non-linear systems, but running just the monotonic analysis. We should be running the full hysteretic in order to find what is the real capacity of those connections. Similarly, we looked at the panel zone deformation, and we found out nicely that the ones that they have, the ones at the bottom are the ones that they have the biggest web opening. There was very minimal panel zone deformation. So the message that was coming up after this investigation was that if you use medium and especially large openings near the face of the column, then most likely you will not have any problems with the shear panel zone. Again, the critical opening length is very important for the strength degradation. So the higher the critical opening length, the higher is the strength degradation that we observed. And similarly, getting the same picture, we saw that different scenarios, they may give us different results, but we can identify from the very beginning what is happening in terms of ductility. And I have highlighted that all the models that we've run, when then compared with the connections using solid beams, we found out that the maximum panel zone deflection was reduced slightly or reduced quite significantly, depending on what is the connection that we're having. But the worst case scenario was always the connection without having any sort of opening. Again, if we were trying to correlate the monotonic with the cyclic, we found out that the monotonic analysis always overestimated the rotational behavior, which is not good, obviously, and we have to make sure that we run the cyclic full hysteretic performance. Same picture as before. The only thing that is different is that now for these type of connections we're proposing different openings to be used as the ideal ones. Looking at the bolted connections with isolated as well as fully perforated openings, we again found an experimental work from the literature review. We validated our models. We used the elaborated model then to do the parametric study and come up with all the conclusions. I have to say that we had discretized everything, all the components of the connection, including the welding, contact elements. It is worth to mention that these connections, when you run a full hysteretic behavior, which means 32 cycles, 64 monotonic analysis, and you have all these discretized models of the bolts, the nuts, everything, you're increasing a lot the time of the analysis. So we're talking about an analysis which may run for a week or two on a high performance computer by the time that you press the button. So it's very time expensive analysis. That's why we have to make sure that we understand what's happening and then propose design methodologies so practitioners, in fact, they don't have to go through that process. As I said, we looked at isolated openings as well as two openings next to each other, very closely spaced to each other, and then also the fully perforated beams, and we compared everything with the connection using solid beam. The global picture looks pretty similar, which it is in fact very good, because we can certainly say that, that there are no hidden things there missing. So we got the similar behavior, but in the case that we use the fully perforated beams, in that particular design with that particular connection, the capacity of the connections using the perforated was decreased by 10 to 15%. So it was one of the messages that we got from that study, which were around 20 different models looked at. Then we're trying to play with the parameters, in fact, and what we did, we had a beam which has the full perforated openings. The part of the beam was moved quite away from the connection to see what is going to happen in that case, and you can see that there is no energy dissipated in the connection, so very few stresses have been concentrated in the vicinity of the connections. No plastic hinges are formed in the edges of the openings. Those particular ones, they failed in lateral torsion buckling. The energy, as I said, is not dissipated. The capacity is very low. So if you use perforated beams and you're trying to move away the first opening from the face of the column, in fact you're not designing an RWS connection. When we moved the first opening a bit closer to the face of the column, the capacity was increased and we dissipated some energy. So now it's pretty clear to us what we need to do in order to be able to control that plasticity and which ones are the ideal positions, sizes and shapes of web openings to look at for very precise analysis. Obviously, it couldn't be missing the composite design as well. So we looked at the WUFB connections, these post-Northridge connections, to see what's happening also when we have a fully composite scenario, and we discretized the full model using the shear stats, the mesh, concrete and everything, and according to an experimental result that we found in the literature review, using a trilinear material model for the beams and columns, multilinear one for the concrete. That increased a lot, again, the time that we needed in order to do all the analysis, and the stiffness and the stance were just simply modeled by a bilinear stress strain model. We run now another protocol that comes from the Eurocode 4, and also it complies with the American Institute for Steel Construction, and we got that our model, it actually behaves very similarly to what is happening on the experimental result. Again, we've looked at more closely the concrete, how the concrete behaves, and we found out that again our final model is precisely demonstrating all these cracks and crashes that we get on the concrete. We then ran a parametric study of 30 models. In this case, we only changed the end distance S as well as the depth of the opening, but the shape of the opening was always the circular one. But we ran everything as composite and non-composite to see the interaction of the concrete, whether it will change anything in our design. So what you see here is pairs of the same connection. In the left hand side is always the non-composite one, and the right hand side is the composite one. Now surprisingly, we found out that the concrete, although it helps towards the capacity of the perforated beams, it doesn't really help in terms of the effectiveness of the RWS connections. So because of the concrete existence, the stresses were distributed in the shear panel zone as well, and not too many stresses were concentrated in the vicinity of the opening, which was in fact an opposite to what we're trying to find. That was really interesting. So we keep doing more and more analysis, but you can say, and you can see straight away, for instance by looking at this one, that the shear panel stresses have been mobilized effectively in the vicinity of the opening. Once you have the composite, you have fewer stresses there and more stresses on the shear panel zone. So that was a very critical point, because we know that always we will have a downstand beam and a concrete on top. So all that knowledge that we have used so far, and the software are giving us, and the design methodologies are giving us, in fact have to be adjusted to the composite actions. So we looked at more precisely what's happening if we do not have openings at all, and how the stresses are distributed in the vicinity of the connection, and if we have a small opening located away from the face of the connection. And as we anticipated, there was not much difference between the two. However, when we moved that opening closely to the face of the connection, to the face of the column, and very close to the connection, we got a flange buckling mechanism being formed, when we had slightly bigger and even bigger openings at a fair location, a fair distance from the end of the connection and the face of the column, we got another failure mechanism. So all that is telling us that we have to be very precise when we combine those dimensions, all these geometries. Either that is the distance S with the diameter of the opening, or the shape of the opening with a specific critical opening length with a distance S. As a result from that study in terms of composite, the composite contribution that we gained in the positive direction was up to 65%. So in terms of the capacity of the connection, it was increased that it was expecting, and in the negative direction was up to 31%, with not much difference when we had small, very small openings. And as the protocol, the SAC Joint Venture is actually proposing, we should also do all these analysis on a frame. So we ran some pushover analysis, non-linear static analysis, and we also looked at the incremental dynamic analysis to replace the time history, the full dynamic analysis. We used a particular footprint of a building. We found in the literature that it was used extensively, and we had a 4, 8, and 16-story building. Then we managed to come up with a stress-strain curve for the monotonic and the hysteretic model, using the composite as well as the non-composite scenarios. We ran 20 different earthquakes with magnitudes from 6.5 to 7.5 Richters, real earthquakes that happened obviously in the past, and we produced the incremental dynamic analysis curve. So I have to say that we're talking about 4,500 dynamic analysis, which are produced in 120 IDA curves. So a lot of work behind this research, and we were very pleased again to see that the behavior between the RBS and the RWS frames was quite similar, because in that case we can say that we can introduce our RWS connections and the connections using perforated beams in Eurocode 8, which at the beginning was a no straight away. When we in fact worked out the median IDA curves, we found out that for 4-story buildings and 6 and 8-story buildings, the RWS frames behaved better than the RBS, but when we looked at the 16-story frame, the RBS behaved slightly better than the RWS. When we looked at the probability of exceeding of all these results and trying to understand the spectral acceleration, having a 5% in this case damped spectral acceleration, we can see that certainly for the first scenario, for the 4-story buildings, the RWS frames behave much better than the RBS. The RWS is better. So the highlights of all that study, as I said, the long study, is that in the elastic region, RWS and RBS connections, they behave similarly. When we looked at the roof drift ratios, the RWS connections demonstrated a better strength performance. In terms of the capacity and displacement ductility, RWS connections are ideal for low-story buildings, 4 and 8-story in our case. And for the 60-story buildings, we could use RBS instead. All that work has been, we have tried to come up with some design recommendations, obviously, make it simpler for the practicing engineers, the ones that want to design such connections. So we started looking at exactly what the Eurocode 3 is proposing, Part 1, Part 8, and what the Green Book is proposing, and merging that information and adding all the extra bits that we need in order to account for the perforated beams. The most important check that we have to introduce now in our analysis is the one for the veer and tilt bending at the reduced web section. So we're not looking at web post buckling or other failure modes associated with perforated beams as such as the veer and tilt bending. Obviously, the veer and tilt bending is dependent on what is the shear moment interaction. So as I said at the beginning, when you move that opening along the length of the beam, things will change. So a simple, I would say, it looks quite complicated, but it's a simple, in fact, a step-by-step methodology that we're proposing and highlighting certain steps, like we start always with a calculation of the moment capacity of the reduced shape, reduced web opening section, and we have to find that this MPLRD. In fact, we need to work out what is the plastic moment capacity of the top T section and the bottom T section, and what is the lever arm between. And once we have that, then we can move on to the calculation of the shear at the web opening center line. P355 is actually proposing the methodology how to find the plastic moment capacity at the reduced section, so we can adopt that one. And then we have to work out what is the rotational capacity of the column web shear panel zone. Moving a bit further on, we have to calculate the rotational capacity due to yielding and bolt bearing of the shear tab. Then very important is the step where we calculate the additional deflection that we have due to the existence of the opening, and especially if these openings are quite large, we will get quite a lot of local deformation. So we have to calculate that local deformation and add all these local deformations due to the number of the openings that we may have if it's a fully perforated beam. And as a last step, we have to work out the rotational capacity of the entire connection by just adding all the rotational capacities that we get. So synopsizing all the research work that we have done so far, and as I said, there is a lot to be done in the future. We can certainly say that large isolated web openings can prevent the excessive shear deformation of the shear panel zone, so we can alleviate the stresses from the connection and we can move them further away towards the beam, so we can effectively talk about this weak beam strong column scenario. The RWS connections, and especially the ones with the novel openings, they achieved high inelastic rotational capacity, so we managed to reach this 0.035 radians that is proposed by all these American codes. In fact, we've reached the 0.05 level, and nowadays we're working on reaching the 0.07 radians level, which is proposed by the DoD and the GSA in the United States when we talk about progressive collapse and catenary action. The connections that they had beams with novel openings, they behave better in comparison to the circular openings, because we could actually control the capacity, but also they behave better in terms of the stress distribution. RWS connections are the ones that we examined are ideal for low-story buildings, at least the research we have done so far. This is the message that it comes up. And RWS connections, and particularly those with novel web openings, as I said, they can give us this ideal design if we play with the geometric parameters accurately. So we can certainly say that is a better design because we know what is happening, let's put it like that. Now the key parameters are the critical opening length, then is the end distance S, and then is the web opening depth. I understand that most of them, when they see them, they get a bit of surprise, because they would have thought that the web opening depth is in fact the most critical one, but it's not. The critical opening length is the most important of all when we see the big picture of the results. And similarly, I would say that the web opening area is not a parameter that we have to worry about much. So how much material we actually remove is where the material is. A few current projects, I mean, we're trying to introduce, as I said, all that to the Eurocode 8. In order to do that, we have to go through the experimental work as well, to validate all our results with, to duplicate our results with experiments, although we have validated the results with experimental that happened in the past by others. So the next 2-3 months, fingers crossed, we will be doing this experimental work, and we'll be able to introduce the RWS connections and the RWS with fully perforated beams into the updates of Eurocode 8 by 2020, I believe. Another very interesting study is investigating all that, but using gigantic connections, because in those connections used in high-rise buildings, for instance, we may have to go for the plate girder design, which has a lot of welding. So all that happens because of the welding problems. So we have to investigate all these things again, whether they will apply or different factors have to be used. So again, some members of my research group, they work on gigantic connections, very interesting. And more importantly, the pre-engineered fuse connections. So we're trying to make sure that when that part of the beam is stressed a lot locally, then it can be replaced after the earthquake event. So we have to make sure that there is a mechanism there that it can hold the structure, hold the connection, and we can remove the damaged part and put another one. Exactly the same with the fuse system, fuse concept. So I would like to almost end the presentation, obviously, by thanking all the partners and the funders of that project all these years, the last decade, including the ISTRAC team. And obviously I would like to acknowledge all the people that they have taken part in these projects. So some of students, current students, some of them have already graduated, they work out there, and some